Okay, great. Okay, good. Welcome back, everyone. This is the 7th pseudo lecture of an indeterminate number this summer. Today my plan is to really get to the key thing we're supposed to be talking about, which are basically varieties and schemes. So now, after today, if all goes well, you'll really rigorously know what a scheme is, and you'll really basically know what a variety is, or things more general than varieties, to begin to work with them. So what I'd like to do is get to maybe the most serious concept of the hour is going to be checking something as a sheaf. But I'd want you to appreciate it more. So instead, I'm just going to do some examples to, first of all, make sure we know where we are, and then we'll be well set to see why this thing is a sheaf. Okay, so here is an example, and let me see whether I should do that. I'll remember to update. Okay, so here's where we are. So let's consider this ring. So I wrote down a not so random ring, and it's a ring that lots of people will recognize and know and love. And so what happens when you see a ring now is you should feel like you have to draw a picture. There should be something you have no choice, but you have to drop what you're doing and try to figure out what this thing looks like. Okay, so let's try to do that. So we'll look at this. We're trying to draw a picture of a ring. And so we could do this inside mSpec or Spec. So let's do mSpec for now and worry about the bonus points later on. So then let me give myself something to write with. Okay, so in C4, which we're thinking about as mSpec of the complex numbers adjoin W, X, Y, Z. So inside that, what we're really trying to do is just solve some equations. That's all we're talking about. Maybe even before I say anything, I should say that secretly, you could replace the complex numbers by any field in what we're doing here. So the complex numbers is only for psychological happiness, to make sure that you are feeling comfortable with that. Okay, so the question is, what are the solutions? And so what you do when you have to solve some equations, you either just go ahead and solve them, or in this case, if there are infinitely many solutions, you might just write down some solutions. Actually, maybe I'll just ask the people, the shepherds, if they're game, to just give me some random solutions, since I really will bet a lot of money that the shepherds can name solutions very quickly. Or maybe they should look at the form of the equations first, and then they realize that is something. So W, X, Y, and Z could be equal to a 4-tuple. And an example of such a 4-tuple, I feel like that maybe I shouldn't put the shepherds on the spot. And I'll even make it easier by giving one single example, which is 0, 0, 0, 0. Or at least maybe I made it. Maybe that was not so nice because I took the easiest one. And then, okay, ones. Here's another one. What's that?
All ones, I think, right?
All ones works, great. 1, 1, 1, 1. Great, okay, so Julia took actually the second easiest example. And now the next example will make all the answers clear. So I will say 1 now. So how about 1, 2, 4, and 8? And you'll see that this maybe that gives the clues to what's going on. And I'll do another one, which will be maybe 9, 3, 1, and a third. So basically any 4 things in that form a geometric series. And I have to say basically, because you may have to have some special cases to think about, is going to be the solution. And if you just realize how you would solve this in real life, is you, after thinking of some, you just try to solve just solve for each of the variables in terms of perhaps another one. And so what picture, oh, maybe I should say, when I say let's do Juliet solutions of that, really we're talking about W minus 1, X minus 1, Y minus 1, and Z minus 1. That's of course the point that we always translate that maximal ideal to the point 1, 1, 1, 1. And now I can draw a picture. And so first I have to draw a 4 space. Worse than 4 space, I have to draw a complex 4 space, but that's okay. That's 3 space and there's 4 space. So now what does the thing look like? Well, I don't quite know how to draw it, but I can kind of see that if it's going to be like an geometric progression, it's like, it's going to be something which is going to be, also I should say if there's one solution, W, X, Y, Z, I could double my solutions and it's still a solution. So I'm going to get something, whoops, go away. cone-like. And you might believe, so this is meant to be a cartoon, which is incredibly, we don't understand this very well at all yet, but you should maybe believe after some thought that this looks like it should be a surface, whatever that means. Maybe it's manifold-like, perhaps, I don't know. So, but that's what we're looking at. And we've now made a picture of mSpec. So that makes us happy. Okay, and we even know it is a topological space because maybe let me keep this picture as a work of art. So I will keep it. You're welcome afterwards to frame it and hang it on your wall. But there it is right there. And this thing is a topological space as well because we know, for example, the closed sets, you could sort of say, where's W equals 1? And I don't know, there's W equals 1. So that, you know what the closed sets are. And so, so we, in some sense, so we know also what the functions are on it. And we even sort of know what this is part of the sheaf of functions on it. It's also true that this has no nilpotents, no non-zero nilpotents. And so, in fact, all the functions are determined by the values at points. So it's something that, so they're all polynomials. Those are the things that are declared to be functions. And we know that they're determined by their values, so it's not such a scary thing. And also, if you prefer to think about it as a complex analytic space, you know what it is. It's just inside c to the 4 cut out by this equation. So once again, nothing super complicated. Maybe I should say as a complex analytic space, you need to know what the sheaf of functions is. And they're just the restrictions of the complex analytic functions to this set. The functions are determined by the values of points. Okay, so you know all this, and maybe a rhetorical question right now is if you buy it as a complex analytic space, you could ask, is it a manifold? And you could, so that's our space. And a sample open set is in our topology. Let's take as an example would be one of these basic open sets where a certain function doesn't vanish, and that's what the D is for. And let's take where W doesn't vanish just as an example. So these are the points where W is non-zero at our point P. Okay, so let's look inside that open set. So to look inside that open set, we have to invert, that corresponds to inverting W. We've checked that the open set corresponds to exactly the points of this spec. So let's just work out what it is. I'm going to write down that when you're inverting W, you can formally add something you might want to call 1 over W. But just as a useful tip, it's nice to just formally add something which is 1 over W. So I'm adding a new variable A, and I'm requiring A times W equals 1. And now this ring is this ring. I guess I could put specs up front. So let's okay. So let me just show you that you can work with this ring. So we have our initial ring where we're looking where W doesn't vanish, and I wrote it down in this way. And now let's actually just do the algebra. So okay. So the first trick I'll do is that because W is invertible, and its inverse is A, I could just change the first thing to be Z minus AXY, and then everything else is the same. So in other words, I just divide it by W, and I'm allowed to because W is a unit. But now, if I've done that, Z is just determined by all the rest. So I can just forget Z in my list. So W, X, Y, and A. And now I just forget Z because Z is just AXY. And I get WY minus X squared. I get, there's a Z there, but that's AXY minus Y squared, comma, AW minus 1. So I hope I did my algebra correctly. And now, what will I do next? Oh, I might as well divide by this W and make it Y as AX squared. And now Y is just determined by the others. So in my algebra, I could just forget the Y completely and just replace it by AX squared up everywhere. So that's gone. And this turns into AX squared minus AX squared squared, comma, AW minus 1. Oh, that's zero. So that's gone. And now I just get C adjoined W and X and A, where A is the inverse of W. So I'll just put it back in this form. So here's what we've discovered, because the algebra just kind of collapsed to something nice. This is just the WX, when I take spec of it, this is just the WX plane. That's the picture I get for this. but I'm throwing out where W equals 0. So minus the x-axis where W equals 0. So that's the algebra that we did. And now I want to point out the algebra we did was exactly the same. It was basically how you would solve this if you were thinking geometrically. You would, so basically what I'm saying is if you want to get all the solutions where W is non-zero, then you just take any non-zero W and any X at all, and that's going to give you a solution. And then you can work out A is 1 over W, Y is AX squared, somewhere in there, I think, and then Z is whatever we said it was, maybe AXY. So the solving equations equals the algebra equals the geometry. So that that is so if I do, there we go, I should do it like that. So if you have a spec of this ring, then where W is not 0, you get the WX plane. And so what you've really done is you've projected to the WX plane from this thing in force space, and you get something which is an isomorphism, whatever that means, although we're very close to knowing what that means, away from where W equals 0. So we have a really good understanding of most of this variety, and most of this thing. And now I can, for example, tell you that it is a manifold. If you don't want to think complex analytically, where W is not 0, because I know what it is as a ringed space. As a ringed space, it looks just like the WX plane minus the W axis. So where W is not 0, it's a manifold. And then you could, or if you want to think about it, if you're more arithmetic, you can try to find solutions. Forget the complex numbers. Let's do solutions over the rational numbers. Well, you now have enumerated all the solutions over the rational numbers where W is non-zero, and you've explained, and this will give you a recipe for doing it. So how about where W is 0? We might as well understand the part of this thing, this variety we have not talked about that we've yet to understand, which is, well, where W is 0, this is going to be a closed subset. And how do I work out what that is? I'm just going to take the same equations and just set W equals 0. And when I do that, everything with the W disappears, and I get this set, this topological space. So this topological space, well, how do I picture that? Well, once again, I'm just going to solve equations. And if I said in 3 space, which I can somewhat more visualize if I pretend it's not the complex numbers, if I said solve the equations where xy equals 0 and x squared equals 0 and xz equals y squared, then the first thing I would notice is that, well, if x squared is 0, that means x is 0. And so for experts, we've done something bad to the algebra, strange to the algebra, but for everyone, the topology doesn't care about nilpotence. We've already discussed. So now x is 0, but that means for free, xy is 0. And that is going to disappear as well. And so I might as well just write this as spec adjoin, c adjoin. I'm just going to get rid of the x because x is 0. And I get c adjoin yz. And what's my last equation? Y squared is 0. But then if y squared is 0, well, that's the same as saying y is 0. If I only care about solving equations, so I can forget about the y. And so, in other words, what's left over is going to be, what's the complement of, I had the wx plane minus the w axis, that's most of the points in the set, but and the remaining ones are just a copy of the line in some sense. And so if you want to find all the rational solutions, this is not going to be hard, for example. Okay, so that was the example that I wanted to work out fairly completely, because really in the end we know it is a topological space. We're going to be able to figure out what the rings are. Actually, maybe let me go back one thing and say we looked where W was not 0, and everything was kind of symmetric, and we could have instead looked where Z was not 0, and using that we'd see this entire thing is a manifold except at the origin, and something strange is going on at the origin. So this is something, and for super experts, this is a cone over a twisted cubic curve. This is a cubic cone. Okay, so great. So now we've got the example, and now it's time to define this the sheaf of functions on spec A. And I don't know whether you want, again, you should feel free to think about mSpec or just think about spec, and there'll be no difference in anything that we are saying. Okay, so so as I said last week, on the locus where a function doesn't vanish, I will tell you what the functions on that distinguished open set are. I will define them to be just a, where I localize at f. And again, this is if you want to, if you have to actually do algebra with it, it can be useful to write it like this. And that will be enough to understand it as a ring space, because we know the sections over the basic open sets, we know how to restrict. And so now we can just go and compute stuff. And I should say, we still need to check that this gives us a sheaf. And because we have, what that means we have to check is why it's a sheaf on this base of the topology. So let me table that, and you can just believe me for now, or don't believe me, it's up to you, but I will pay that off later on. And let's just see what happens if we don't worry about it being a sheaf and we know it's a sheaf. We can just calculate stuff. So, and in particular, you should appreciate that you can just calculate stuff without the messiness of proving things are sheaves once you've done this once and for all. Okay, so let me do some examples. The first example is going to be inside. So we have something which we have a ring space A2, which is going to be a, I guess I'm being very carefully agnostic as whether I'm talking about mSpec or Spec. So the advocates of topoi or topi, or however the ancient Greeks said it, I guess Jonathan says this is topi, and so I'm guessing either he has a speech impediment or he actually knows it's supposed to be actually pronounced in that way. But I'll deliberately mispronounce it as topoi. So the fact that it doesn't matter is relevant, interesting, and why, in some sense, this deserves a name. But it deserves a Greek name, not a French name. So what are the ring of functions on this open set? Well, this open set, how do you work out what it is? Well, you know what sections are over distinguished open sets. And so this open set of everything, that's what my picture is supposed to be. It's the entire plane, except I'm going to throw out the origin. And so this thing is the union of locus where x doesn't vanish and where y doesn't vanish. And so how do we find functions on the entire thing? Well, where x doesn't vanish, we know what the functions are. They're polynomials where we're allowed to have x's in the denominator. So we're allowed to invert x. And where y doesn't vanish, they're polynomials, but we're allowed to have y's in the denominator. And the sheaf condition says we want sections over the union of these two things. Then we need to make sure they agree on the overlap. And where the overlap is where x and y both don't vanish. And there we know the functions are where x and y are both invertible, or x, y is invertible. So what we're looking for, is the data of a function. Let me call it a function. I'll call it a function. It's an element of this ring, and another function which is an element of this ring. And I want f1 to be equal to f2 when considered as, since they're in different rings, when they are in this ring. And so now it's not so hard to figure out, because each of these rings sits inside this bigger ring. And in fact, this bigger ring sits inside even the fraction field of the polynomial ring. So all we're really saying is this element of the fraction field and this element of the fraction field are the same as elements of the fraction field. So the question I'm asking is, which quotients of polynomials can you think of that have no y, they're allowed to have, so they're allowed to have nothing. How can I say this? The only possible denominators they can have from this point of view are x's. And the only possible denominators they can have from this point of view are the y's. But they can't have either of them. So the only rational functions with nothing in the denominator, the answer is just going to be the polynomials. In other words, the sections over the plane minus the origin are only the things, everything extends over the origin. They're all honest polynomials. So, so that was really clean and easy, just because what made that easy and what's going to make things more complicated otherwise is that we're working in an integral domain. And so everything, all the localizations that come up, maybe for pedants, as long as you're not dividing by 0, then all the localizations are inside this biggest of all localizations, the mother of all localizations, which is the fraction field, or the quotient field of this integral domain. So that's the, so in case, for integral domains, that's not so scary. So here's something which is not an integral domain, and let's see how things work there. So one of my favorite first examples of a non-integral domain is going to be something like xy = 0. So it's the union of the axes in the plane. That's how I'm thinking about it. So it's not an integral domain because xy is 0. My question is now, to make an interesting question, let's say the open subset. So V is going to be this non-integral domain. And my open subset, let's just throw out the origin again. So let me erase, let's see if this will work. Erase the origin. And my question is, what are the functions there? But if you look at that picture with the origin, you should believe, and now this is not a proof, you should believe that we have the x-axis minus the origin, union the y-axis minus the origin. And so if you believe that, that means you're predicting that the sections over this will be, well, you just need to choose something over the first open set, a function in the first open set, and a function over the second open set, and they don't overlap. And so, but a different way to say this is, I guess, how can you get rid of the origin? You could throw out the locus where x plus y = 0. And that's exactly cutting out the origin inside here. So that we predict an algebra fact, which is that these two things are isomorphic as rings. And now you can prove it, and it works. So this is a case of, again, the geometry telling you something true algebraically. And if you are used to thinking algebraically and you're not used to listening to geometry, this will give you a chance to do it. But if you're more a number theoretic person, here's a different example that's also not an integral domain, which is the integers mod 60. So when I talk about spec of them, I need to tell you what it is as a set with a topology and a sheaf of functions. So as a set, it's got 3 points, the prime 2, the prime 3, and the prime 5. So I'm picturing this as sitting inside Z, in spec Z. And now with the topology, if you could see where functions vanish, and there's a function 15 vanishes on these two, but not this. So that's an open set. And similarly, that's an open set and that's an open set. So the topology is discrete. And now the sheaf, what's the sheaf on it? Well, I'll let you think about why that's true. But it's Z mod 4 here, Z mod 3 here, and Z mod 5 here. And okay, so if that's the topology, and that those are the sections of the open set, then that means that the sections over everything, which we know are supposed to be Z mod 60, is going to be sections over this, and sections over this. And so it's the Chinese remainder theorem. So the Chinese remainder theorem is somehow embedded in this. It's mixed up in this, it's entangled in a way, it's hard to disentangle it. And the proof that things glue will also be very Chinese remainder theorem-esque. Okay, so that is, okay, so now it's time to actually define stuff. So so what's an affine scheme? I'd want to say almost the first approximation, it's spec A. It's a spec A. So just to be a little bit careful, let's just say it's a ring space that is basically spec A, which means it's isomorphic to spec A, which means it's a homeomorphic, like this, the sets match up, the topology matches up, and the rings match up. And then similarly, in affine varieties, an mSpec A for something that you're allowed to take mSpec of. So it has to be a finitely generated algebra over a field. But now I have one extra condition just to make it fit the classical picture. That's why this definition is here, that it has no non-zero nilpotents. And so that, in other words, functions are determined by their values at points. And you could say, why am I making these definitions? This is the first one's a nice clean one. Why am I making this messy second one? It's because I'm trying to fit this to some older notion. And maybe to fit the geometry and the algebra together, here's a question, which is if A is a reduced ring, if you want, it could be your mSpec case if you're thinking about varieties, then if it's a reduced ring, that means there's no fuzz in our intuitive pictures. So, and then the statement is that if it's a reduced ring, then you can show that it's in fact an integral domain, which is an algebraic statement, if and only if it's irreducible, which is kind of a geometric topological statement. So when I see integral domain, I now picture, my picture is of something with one piece, that's the irreducible part, and it's got no fuzz on it, and that's the reduced part. And so that's how you get a picture from this. Okay, great. So now I've basically told you what I had told you what affine scheme is, an affine variety. And now a scheme, I'm going to deliberately go to the second point. It's easy to see what a scheme is. It's just a ring space with an open cover where the corresponding ring space is an affine scheme. And so that's great. Very fast definition. A variety, annoying thing is we don't have Hausdorff yet. Scheme, we don't care. Variety, people do. So it's again, it's the same thing, which is except minus the Hausdorff condition. So I'll call it a pre-variety, and that's what the ancients in the wilderness in France back in the Stone Age called it as well. Okay, great. Okay, great. So one important thing to check, which is easy once you write, it's trivial once you write down what it is. So you just have to write down what it is you have to prove, which is that if you take in spec A and you take that distinguished open set, and it's a ring space, then this ring space is the same ring space as isomorphic to a spec of A sub F. In other words, the open, I would say that the distinguished open set is in fact affine, and it's F spec of this thing. And what that means is that every open set so, and here I mean by open set, really an open sub-ringed space, which sounds horrible to say, but so take this ring space, take an open subset and take the induced ring space, then that's a scheme just because U is the union of a bunch of distinguished open sets. So in fact, it is covered by things which are so that's good. You wouldn't, I think, like you'd want an open subset of something nice to be nice. And so, for example, we now know that the A2 minus the origin is a scheme, or a pre-variety if you want, because it's the union of two affines. And now one thing I should say is now we have an example of something, a variety or a scheme that is not affine, that is not a spec. And maybe this is worth saying why, just so you have provably an example of something non-affine, but so you can see really some of the ways to think about this, which is if it were affine, the thing about something being affine, if I give you an affine scheme, which means a set with a topology with a sheaf of functions, you could recover the ring it's spec of by simply taking the functions on the entire space. So then if it were affine, then A would be the functions on, let me call this thing V, on the entire space. But we already worked out what that was. These are going to be just, I forgot what field we're working over. So I'll work over an arbitrary field because it doesn't matter. Then that must have been the ring. And better yet, once you know the ring, you can identify the points by looking at prime ideals. That was how, so it's not just that they were associated prime ideals, you can really recover them. So for example, the prime ideal x minus 1 comma y, you can recover by just solving x equals 1 and y equals 0. So, okay, so in that case, here's a maximal ideal. That's prime for sure. Let's solve those equations. We get x equals y equals 0. And so we should get a point. But on V, because we threw out the origin, this has no solutions. So it cannot be an affine. That is worth digesting to realize not much happens there, but it really lets you know the extent to which everything about this affine scheme, which looks really complicated because it's got topology in it, it's got sheaves in it, is nothing more than the ring. It's in a very natural sense, literal natural sense. Okay, so that is an example of, that was an example of something non-affine. Here's something which is not Hausdorff, even though we don't know what Hausdorff is. I'm going to convince you it's not Hausdorff. I won't prove it. I can't prove it because I don't know what that means. I know what it means, but you don't know what it means officially. So here's something which is not Hausdorff. What I'm going to do is I'm going to take two copies of the line. And again, you could feel free to put them here if you feel like it. And also, I should say, this is the complex numbers. There's nothing about the complex numbers are important. You could put a field there or even an arbitrary ring. And so what I want to do is I'm going to take the affine line. So there's my first affine line, which is the T line. And here's my second affine line, which is the U line. And I want to glue them together to get a new ring space. And here's how I'm going to glue. I'm going to take this. It's going to be like a sandwich, or maybe I feel like it's more like when you're sticking some sheet protector on some screen protector on your screen, and there's a bubble in the screen, and somehow you can't get the bubble out. And that's what's annoying. Ideally, you want to put glue everywhere and have it stick. But I'm going to add glue only away from the origin on the T and away from the origin on the U. So my glue is green. And so that's away from the origin on the T line, that's away from the origin on the U line. And so to identify them, I'm going to give you a ring space. And that ring space is going to be every open set it's going to be the union of, it's going to have an open cover by this thing and this thing. and they will intersect on the green. So I need to somehow glue the points where things are being glued. I need to glue the topology. I need to glue the sheaf of rings, and that sounds like a pain in the butt. But no pun intended. But the way to do that most cheaply is to just say that these are both specs. It's a spec. So as long as I make these rings, identify the rings, I've identified the ring spaces and I've glued them. And so the ring here, C join T with 1 over T and C join U with 1 over U on this side. So as long as I tell you how they're isomorphic, I have told you how to glue them. And if I show you those two rings, obviously the isomorphism I would pick. The only isomorphism any reasonable person would pick would be T and U are glued together. So I do that. And so there's my sandwich. I squish my sandwich together and it's got a bubble in the middle. And the picture I have when I glue the points are going to be, I have the T line and the U line, and all the points are associated, except at just one point here, they're really 2 points. And so that's my picture of something non-Hausdorff. And that is almost, you can almost make that, that's almost a theorem. That's a valid criterion of separatedness, that that all non-Hausdorffness is of this form. Great. Okay, next examples, super important examples for classical reasons, projective space. So what is projective space? I never know whether this is something that people learn when they're 3 years old, or no one knows it. I'm guessing that it's closer to no one knowing it. But I know many people who are watching this know all about it. But just to be clear, here's how I think about it. So the idea, which is not going to be, the point is to make these things rigorous and turn them into geometric spaces in the sense that we want. But as a set, we should think about it as one-dimensional subspaces of R to the n-1. So for example, in R3, I live, I guess many people live in curved space-time, but I live in R3, and so and there's the origin in R3, and if I take all the lines through the origin, all the one-dimensional subspace through the origin, that is RP2. And so the magic, I don't know what you think of it as magic, but I've just told you what it is as a set. But even better, it can be endowed with this nice structure of a manifold or a variety or scheme, if you know what that is, which you do. And also, there's nothing important about the real numbers. And in fact, I feel more comfortable with the complex numbers. I guess I told you I live in R3. I really live in C3. And so that is actually, hold on a sec. I wonder if there's one thing more I want to say. No, I think I'm good with that. Great. Okay, great. So so a useful picture is that RP2. I'll have to do this visually. RP2 has nice big open sets. It's like a compactification of R2. And here's how you compactify. Here's where you see R2 and RP2. Again, I have the origin. I can throw all the lines through the origin. One way of thinking of points, I could just take triples of real numbers, and I want to identify a triple of a real number with any non-scalar multiple of that triple. And that's what I'm describing as a set. But how you see R2 inside it is, well, almost every line through the origin meets the ceiling. And so I can identify almost all the lines through the origin with points on the ceiling. It's a one-to-one correspondence. And so I identify the lines with that even manifold. And you may think that that's great. You're happy. Now you understand RP2 completely. But how do you really know it's the same manifold structure if you don't pick different, if your ceiling isn't tilted or if you use a wall instead? In any case, that's the idea. And now we can try to endow this with a geometric structure. And now let's do this with just P1 to start with. And it's really the same algebra as before, where I'm still going to glue A1 to A1. And so here's my T line, and here's my U line, and I'm going to even add my green glue to the same spots. And now I'll glue them together by giving you an isomorphism. But now I'm going to do something different. I'm going to glue T is going to be 1 over U. And then that certainly is okay. That still gives me an isomorphism of these two things. So what does that do? It glues the point T to the point 1 over U. That's what it does on points. And so what you've done is you've basically glued together there's the T line, it's kind of, and there's the U line, and now they're kind of glued together in a different way. And now you get something which is Hausdorff. And so what are the points of this thing we built? Well, let me go back. If you're just talking about mSpec, then you have your T line, and then you have your U line, and you're gluing most of the points together, except you didn't, what happened to U equals 0? You didn't glue that point. And unlike last time, as U gets closer to 0, you should think this T is going to infinity. So you've really added a point at infinity. So we have that picture. But how about if you, now let's go and add generic points. Well, there's only one extra point on the T line if you want to think in a scheming way. It's the generic point of C. It's this overlay, this point that's somewhere on that line. And it's glued to the generic point of the other thing. So CP1, so P1, the scheme, has an extra generic, has one generic point, and it's for the entire thing. And then just to really show you we can do business with this scheme, or with this variety, I will tell you what let's work out all the functions on P1 are. So what's a function on P1? Well, because we're talking about sheaves, we want a function on the T part, like the northern, well, everything but the south pole, perhaps. And we want a function on the U line, everything but the north pole, and we want them to agree on the overlap. So in other words, we want a polynomial. That's what we declared the functions were here. A polynomial T and a polynomial in U, and they better agree on the overlap, which means that f of T is G of U, but U is 1 over T. So if I asked you for a polynomial f and a polynomial G, so that when you plug in f of T, you get G of 1 over T, if you think about it, the only way to get any, if it's possible, is if they are both constants. So in other words, on a sphere, on CP1, the only functions will be defined functions are constants. And if you're happy with Riemann surfaces, you know that a Riemann surface, a connected Riemann surface, the only functions are constants. And this is the same fact, although said somewhat differently. In the same way that we did a Hartog's type thing before, now we're having a maximum principle type argument now. Okay, so now for projective space more generally, and here my point of doing this is to also try to sell you on something notationally which I find convenient, because otherwise, if you do projective space in a painful way, you have subscripts and superscripts and letters coming out of your out of I don't know, your nose also. So the idea I want to do to have good notation, this is, I guess, in mathematics, you always, good notation, like names matter, and good notation matters because it tells you what's true. So the idea we're going to have is that the idea of projective space is supposed to be that we take n+1 space and we take this quotient. So an n+1 space might have coordinates like this. But we can't, so there's our picture of if we're in R, I guess it's more like R2, and P1 are the lines through the origin. So then you can have these coordinates, but you really only want to be able to talk about quotients of 2 of them, because x0 is only defined up to scaling and xn is only defined up to scaling. So they differ by a non-zero scalar. And this dumb fact, well, it's not so dumb, but it's even way less dumb than you think, because later on it's going to grow up into being talking about sections of line bundles, but we're not there yet. So let me now tell you the things I'm going to glue together to get projective space, just like, for example, when we talk about P3, we're going to have 3 covers, which will be, if you want the coordinates on my ceiling, the coordinate on my left wall, and my coordinate on my back wall. That somehow every line through the origin has to meet at least one of those 3 things. And so hence, I'm going to cover projective space with these 3 nice things. So what are the pieces? They're each affine space. And I'm going to take my definition. So I'm doing this with an arbitrary field because it doesn't really matter. That's the K here. And my coordinates, I need to pick n coordinates, and I'm going to call them on the locus, I'm going to call them these. And I want to think of this as being x, I over j that's something I'm going to use and rigorously define. And I'm going to take the quotient of 2 things, which I'm not currently rigorously defining, the things I'm secretly imagining that they're trying to represent. So my first open set is going to be something of this. And more generally, the ith standard open set will be similar. I guess to make life easier, to help my notation be slightly cleaner, I could write the same thing down and avoid and say something like there is no I comma I here. But maybe if you want to make it a little bit easier, you might just toss it in gratuitously and set it equal to 1. And that will be in keeping with how we're supposed to be thinking of it. So now we have, it's still n space, but now we have n plus 1 variables. One of them just happens to be 1. And now how do I glue them together? I'll tell you how to glue 2 of them together, but that's not exactly enough. With P1, there are only 2 to glue together. And you have to think about what you need to do to glue together these ring spaces to make one ring space. And one of the exercises I asked you to do in the past, or suggested you do in the past, was to say that to glue together a bunch of ring spaces, you only need to say how they glue pairwise and make sure that in triple intersections, you didn't contradict yourself. So what's the gluing? I'll tell you how to glue UI to UJ. To do that, I need to tell you how to glue these rings together. So I'm going to glue the UI one looks like this, and the UJ one looks like this. Oh, and that is, I guess I should have inverted something. And I'm going to invert, because I'm not gluing the entire thing. I'm going to invert X, J, or I, and I'm going to invert X, I over J here. This is just like the P1 case. And then I need to tell you what that ring isomorphism is. And what I will say looks, if I said it differently, it looks very clever, but I'm hoping you won't think it's very clever, that the X something over I on this side gets turned into things over J here, just because we're thinking of, just because of how we think of each of these. So somehow our intuition is telling us precisely how to glue, and then you can check and should check that as cheaply as possible that they glue without any problem. Great. Okay, so we have lots of examples, and maybe the really important thing I'm going to say is often one says, like, people think with varieties and schemes that, you know, if only there were some basic examples you could work through. Well, these are basic examples you can work through, and I feel you have to. The thing about basic examples is you can't just watch them. You have to actually think about them and try to figure out what you're confused by. So I really would encourage you in Zulip, and I'll try to pick problems that will help push you to do that, to ask each other about examples that you want to understand and realize you really can answer any question, such as I give you some crazy variety, and in theory, if I give you an open set, you can work out the functions by just simply working out elements of rings that happen to be. So unfortunately, to make all this work, we need to answer the question of why this actually does define a sheaf. So all that's missing to make all of this work is just to have these things form a sheaf. So, and again, the idea, which I said last week, is that we declare on every open set what the, since topologically that's spec A sub f, we declare what the sections are, and we have to worry about whether it's well defined and why it gives a sheaf on the base. So the trick, as I mentioned at the end of last time, is that rather than, I could have said this is that the sections over the distinguished open set are A sub f, and instead I define them, I define it differently, where I allow myself to invert everything that I can divide by anything as long as it doesn't vanish in this open set. And so in other words, in the plane, if you were to look at the distinguished open set where xy is non-zero, then you're allowed to divide by x to the 7th, but you can't divide by x plus y. And the handy thing about this, the great thing about this, is you're defining what's going on without reference, with reference to the open set, but not the particular f. It's independent of choice of f. And so the key thing to check, or the key thing that will give you the insight as to how this works, is that in fact this is the same definition, and that's something which is very worth trying out. Okay, so now we have a pre-sheaf on this. We now have at this point we have a pre-sheaf on the distinguished base, and now we're at the problem. Now we can state the problem clearly again, which is that if we were to cover, if we have one open set, we can cover it with these smaller distinguished open sets. Why do we have the identity axiom and the gluability axiom? So what do we need to check? And I'm going to just deal with the case where the original thing you're trying to cover is the entire scheme, just the entire spec. And that's just because it's notationally simpler, and there really is nothing extra that's hard. All the hardness is here. In fact, all the hardness is here even for something else more general. So one thing which is useful later, and very useful later when you want to talk about vector bundles and such things, that if you have any A module, not just the ring A, you can make a sheaf out of not just A, but out of any A module M. And what you produce is a sheaf of O modules. You get actually, I should say it's an O module on spec A. And how do I define the sheaf? I'll just tell you what it is on the base. So on the distinguished open set, I want to define the sections to be just the localizations of F. So it's an A sub F module. And so that tells you, essentially, if I can show you identity and gluability of this slightly more general thing, then for free, it's an O module, because on every open set, it's naturally a module. Okay, so that's what we have to do. And I think I'd like to end in around 4 minutes. So I want to, I will do part of it and then tell you more later on. So the first thing I want to do, as long as we're here, is tell you about is to point out that the structure sheaf, the structure sheaf, or arbitrarily, or not arbitrarily, or alternatively, even of M twiddle of this thing. Oh, maybe I should say, just so you have a fancy word you can impress your parents with, that this is going to be an example of a quasi-coherent sheaf. But all it is a module over a ring. That's the fancy word. Great. So, and the stocks of it, this is something which is, I guess, geometry. We're talking about sheaves on a ring space. So the stocks of it at points is something, or things you already know. So if you have a point of your spec, or mSpec, doesn't matter, and that point corresponds to prime ideal of A, then it turns out that the structure sheaf is the localization, is the local ring. Why is that true? You actually told me this many weeks ago separately, which is, this is the thing which guided even us making the Zariski topology. So I'll let you think about why that's true, that if you take smaller and smaller open sets around P, you might as well be distinguished open sets. You're exactly going to get the recipe for A sub P. And similarly, there's exactly the same argument that if you have an A module, the stock at a point P is the localization at that prime ideal. Indeed, that is a module over the corresponding. Okay. And as a happy algebra consequence, M twiddle, elements of the sheaf, elements of a sheaf are determined by their stocks. So for example, if something is zero, an element of if you have M is an A module, and that means it's a global section of M twiddle. And how to know whether something is zero? That should be true if and only if all the stocks are zero. So now we have a purely algebraic statement that an element of module is zero if it's zero in once localized to every single prime. And you can prove that if you want now, and you either can prove it, and it's a nice thing to be able to prove directly with algebra, or it's a consequence of the geometry. And similarly, hence, if you do this for every element of the module, a module is zero if it's zero, if it has no support. And we defined support earlier, so MP is zero. Okay, so let me end with the identity axiom and a little bit about the globability axiom. So all that's left for us to do is that if you have spec A is a union of a bunch of distinguished open sets, and maybe it's, then why is it that when you take an element of the ring and you map it to each of these localizations, why is that an injection? In other words, why, if I have an element of my ring, if I were to restrict it, why to each of these localizations, why do I know, like, why is that an injection? Why does, if something goes to zero, why must it have been zero? And now let me say, I think I'm going to conclude with this argument because it's a slick argument. So let me, and actually we can do this with a module more generally. So, so here's the question we have, which is, if we have, or maybe I should go back a step, which is, remember, this is, remember or do again yourself, that if spec A is a union of these distinguished open sets, that's exactly the same thing as saying that the ideal generated by these elements of F is the unit ideal. And that is exactly as saying that the unit ideal is the sum of AI, Fi. It's some a linear combination of the F's. Because if one is in here, then the things in here are written in this way, and so that's what it is. So our statement now is that if I have a cover, a spec A, and I've translated that as being a bunch of F's, and hence there must be a bunch of A's, such that this is true, and I have an element, a section over everything that goes to 0 in each of these localizations. And maybe the important thing to say is we're not talking about interval domains anymore. Why is M 0? That's the thing we have to prove. And so here I will conclude by telling you what the proof is. So M over 1 is 0 in this localization. What does that mean? It means by definition that Fi to some power times M is 0 in the original module. That was my definition of what this is. So I know that Fi to Bi times M is 0 for some big integer. B is for big, Bi is for big, I guess. And so now M is going to be equal to 1 times M. But 1 is equal to A1 F1 plus all the way to AN Fn 2 times M. And I'll take a huge power. I might as well take 1 to monstrous power. Actually, let me make it even to be safe. The sum of all the Bi's. And then, but now when I expand this thing out, every monomial appearing will have inside it, one of the Fi's will appear to the power Bi, at least Bi. So I get a sum of some hideous things times Fi to the Bi times M. But now Fi to the Bi times M is 0. So M is 0. So that's the, and the way Sarah had this insight, and this may be where I think this idea might have presumably first come with him a long time ago, which is that this is like a partition of unity. And you're recovering M by multiplying it by this partition of unity, but each individual bit of the will give you 0. So that means that we proved the identity axiom. And what's left is the gluability axiom. And the thing about the gluability axiom is the identity axiom we can just directly do. The gluability axiom, the thing that makes it weird is that I could say a one-line solution for experts that will be completely rigorous and mysterious for non-experts. Or I could say something which is really hands-on and direct for non-experts. So if you say it one way, this is an example of faithfully flat descent, which comes from one single trick. Or if you say it a different way, it's something you just literally write down, as we did with identity. The identity axiom, you literally just build what you have to build. The thing you're trying to glue, you build what it is by building it open set by open set. So I haven't decided which one I'll do. In notes, there is a hands-on version that's there. Actually, later on, secretly, there's a fancier version. And actually, not later on is an even fancier version where there's like one single trick, that one simple trick that makes it all disappear. Okay, so let me leave the hands-on argument for next week, and then, or maybe I'll ask you. I suggest reading it because I think it's understandable, but if not, I'm happy to also explain it. And then next time we're ready. Now we know what schemes are. We basically know what varieties are. We can just go to the races and do stuff with them. We can talk about line bundles. We can talk about, so the first thing I want to talk about, I think I will deliberately go in a different order than in the notes, where just for, to be clear, it's not that these things are not linearly ordered. The one important thing is how to talk about properties of varieties and schemes working affine by affine. So the one trick we'll have to go through is this affine p-invocation lemma of how you have the affines talk to each other. And then after that, we can jump in all sorts of different directions, maybe talking about curves or talking, well, many different possible things. So that seems like a good spot to end the formal part, and then we can pause for a bit to let people leave the virtual room and head off to their virtual happy lives. But people who don't have happy lives to go to can stick around, and I can chat and we can discuss things with the thanks very much to the shepherds who will mediate everything. Great, so we'll take a minute or two, and then we can go to Zulip, I guess, and you can type questions on Zulip. Right, I'm giving myself lots of pages to write on. And great, so now I am ready. So where should we start? I don't know whether we should move.
All right. Hey, Robbie, I think you said you were going to have some stories too about Brian.
Oh, no, well, no, the stories I was going to, it's my future intent. I've collected a bunch of quotes from Heart of Darkness.
Okay.
So I'm going to match them with quotes from from Brian Conrad, and but I've yet to. I mean, there's some quotes that just out of. Let's see if I can even. I might even have. You just okay. Okay, here's some great quotes by Conrad. We live as we dream, alone. Or it was written, I should be loyal to the nightmare of my choice. Or I don't like work, no man does. But I'm just reading every single quote. It's like everyone you can imagine Brian saying, no man does. But what I like is, but I like what is in the work, the chance to find yourself, your own reality for yourself, not for others. What no man, other man can ever know. They can only see the mere show and never can tell what it really means. I can imagine Brian saying that. Your strength is just an accident arising from the weakness of others. The mind of man is capable of anything. That's good. Okay, I don't know.
Yeah.
Like more. It's great. It's like I think you know. It just made me very happy. Of course, there's the horror. Oh, we penetrated deeper and deeper into the heart of darkness. I feel like that should be the subtitle of one of Brian's books.
All right. I have, so should I just go with some questions here?
Yes, yeah, go for it.
Okay. So there was a good question. There was a little bit of discussion about what a complete intersection was. And in this cone over the rational normal curve, how do you even see that this is a surface?
Yes. So
there was a lot of questions about how do you see things about these equations. So
yeah.
Another good question that's kind of related to this is, how do you see that it's even reduced? You know,
right. And that's something which I did not say. Right. So this is a great surface. It is a surface, and let me just write down its equations again. Let me even deliberately.
No, I can't see your writing right now. If you are writing, I can't see.
Oh no, that is bad. I realize I have not been updating as well. I apologize. Now, maybe because I switched. Now maybe I shouldn't have gone to the. Can you see anything on the screen at this point?
I can see a blue little squiggle. Now I can see the K's. I can see a blue squiggle. Maybe this is your picture of the, there's the rational normal curve and you're making a cone.
Exactly. It's great how I should say to other people how Taylor was able to sort of just look at this picture and say, oh yes, that's a cone of a rational normal curve. That's a sign that somehow there's like this things are embedded in the, like not many people would look at that and say, oh yes, cone of a rational normal curve. So here are the equations of it. Let's see.
WY minus x squared, xz minus y squared.
And great. All visible?
Yep.
Good. So great. Okay, good. So there are all sorts of great questions there, which I don't want to answer. I will unable to answer, but we'll gesture toward how they should be answered, and they're really important. So one question is, why is it a surface? Another is, one reason to be disturbed a little bit is because you're in something four-dimensional, and this is allegedly two-dimensional, and you have to but you needed three equations. So do you really need three equations or not? So it turns out you do really need three equations. So the questions that is, I claimed without proof that this is reduced, that there are no nilpotents in this ring. I claimed sort of without proof that it's a surface, but of course we don't know what it means to be a surface. We have to define dimension. But if you believe that the plane is dimension 2, and if that's not dimension 2, your definition of dimension is messed up. Then we do know it's dimension 2 away from W0. And we do know, because we've checked that as a ring space, it's A2 minus something away from Z equals 0. That will take care of everything except for that origin, because everything will be covered by those except for that. And so we know it's something which deserves the name. If A2 is a smooth surface, then this is a smooth surface, except we have this one extra point. And so we don't know that it's smooth or not smooth. We have to figure out what we mean. Except, I guess I should say, the participants have already said what the tangent space should be. And you can compute what the tangent space is everywhere. And already you know it's going to be two-dimensional almost everywhere. And then they can check. Like if you're watching and you've done the tangent space example, you can check that this tangent space is three-dimensional. So then you might ask whether it deserves a name surface. So the questions that are open standing questions are, what do we mean by dimension more generally? And what do we mean by smooth or manifold more generally? How do we check that how do we know whether it's reduced? This is something where this may even be an exercise in the notes, but with one crucial hint. The crucial hint is this. I will identify. What's that?
No, nothing. I know what you're going to say. Sorry.
Yes. So the crucial hint, which doesn't come out of nowhere, although it may appear to, is that here's a different. I will describe this ring in a way that if it will make it obviously an integral domain. And so I want to take something that will be just a polynomial ring in two variables, K join AB, except I want the subring where I want only polynomials that have total degree a multiple of 3. So in other words, there's no A, there's no B, but there's an A squared B. And then W will be A cubed, X will be A squared B, Y will be AB squared, and Z will be B cubed. And there's the kind of the geometric series present there too. So if you could show that this ring is the ring I'm describing now, then you win. And again, is that a trick? Yes, it's a trick, but it's because this ring actually matters. It means something. And there's a second thing, which is people who know Grosvenor bases, a more robust general thing. This argument is fantastic because it captures what's very special about this ring. But Grosvenor bases, for people who know what they are exactly the thing that can be used to show things like this are integral domains more general. Okay, so this is something where you actually can do by hand, but also it links to more sophisticated, beautiful things.
I think we're also kind of close to elimination theory as well. So I mean, so, how you convert from one to the other in the general procedures. Yeah. Right.
So and we may actually, I think I want to even go to elimination theory this summer too, to actually in practice see how well. I'm not sure in practice is the right word. In theory, in practice, or in practice, in theory, be able to solve things like this.
Yeah, and so did we talk enough about the number of equations? Something weird is like, should we expect this to happen? Or so if I were to write down random equations, right? I guess you'd expect them to cut down the dimension by 1 every time.
Exactly. So you can imagine. So if you and maybe to set things up, if you are used to manifolds and you have a manifold sitting in another manifold, then locally there's like a little coordinate chart and it's cut up by the right number of equations. It looks like x1 equals x2 equals x3 equals 0 in R in real 10 space, for example. So here you might wonder whether the same thing can be true. Let me give you a hint as to how as to why you need 3 equations. So the answer is, I think a really useful answer, let's see if I can, great. A useful answer, it's like, I don't know whether this is fair to say this, but I will say it anyway in case there's something of value there, which is inside this, so geometry is telling you that really what's going on has to be something about the origin, because everywhere else it's a manifold, and everywhere else somehow manifolds are always cut out by the right number of equations. So let's focus on that local ring. In that local ring, we have a maximal ideal, and m mod m squared is 3-dimensional, not 2-dimensional. In other words, if you were to write down, this requires an algebra check, that if you take this ring, x, y, z, mod these 3 equations, and you take the linear terms, mod the quadratic terms, oh, it's 4-dimensional, I should say. Let me change that. It's 4-dimensional, I was wrong, because all these equations have no linear terms. And so it's 4-dimensional, or if you like differentials, you have 4 different differentials, dw, dx, dy, and dz. And so now, okay, so there are no equations in degree 1, so to speak, up to degree 1. And in degree 2, there are equations. And the number of degree 2 monomials in 4 variables is, I guess, 10, if I added correctly, degree 2 monomials. So in other words, m squared mod m cubed is 10-dimensional. And now the equations are supposed to knock it down. But now these equations are linearly independent in this 10-dimensional space. We have 3 equations, and there's no way, this is now linear algebra. There's no way to do this with fewer than 3 equations. You cannot cut out, in this 10-dimensional vector space, you cannot cut out this codimension 3 thing with only 2 equations. So that's the structure of the argument that will do it. And I understand that that should not be comprehensible, for this is the first time you're seeing it, but the idea really is to look at differential, the fault is in the differential information. And in fact, the reason manifolds work out nicely is somehow also the good thing in the differential information, that you need only work in the tangent space, which is m on m squared. So it's a feature, not a bug, that things get weirder, and it's because we need higher order information. Okay, that's an imperfect answer, but maybe good enough for now.
All right, thank you. So okay, here's another question. So why is it the case that on reduced schemes, f is determined by its value? Or I guess the way you said it is, so why is it the case that f is determined by its values if there's no potents?
Right. So the reason is that if you have the good thing about schemes, schemes locally, the question's about functions on schemes, but then I can ask about functions on open sets, which are affine. So this is about elements of rings. So if we have a ring, the claim is that if I know f mod p for all p, then I know f, but I need there to be no nilpotents. And that's because of this fact, this fundamental fact, that the question is, if I have something, let me just do this the way you often think about kernels. If I have a function in A, and I tell you that it's 0 mod p for all p, I claim that it's nilpotent. And now we come to the statement, the intersection of all the prime ideals in a ring is the null radical, the ideal of nilpotents. So that's an if and only if. So this fact ends up being somehow a very formal, dry algebraic fact at first, but in fact it's this fundamental geometric fact that it's the nilpotents that are the things that are invisible in terms of their values at points.
That's great. All right. So there is another question is, so how do you know that the definition you gave for P1 is the correct definition? I think this is a hard question. That the definition you gave as a scheme is the correct definition of P1.
Well, the great thing is it's not a hard question, because I get to turn it back on the person who asked it. And I'll say, what do you mean the correct definition of P1? So,
exactly. I don't know. So I guess I would have to say what its functor of points is supposed to do. But
then that's because, but then you'd have to be saying that that's the correct definition, right? So as soon as you give me a correct definition, I can prove it to you. If you don't tell me, and I should say that exactly the same thing is with the tangent space. Like, why did the thing I said was a tangent space? How do I know that I used the correct tangent definition? Well, you have to tell me what it is first. And as soon as you do, it's something provable. So all I can do in the absence of being able to have a correct definition is if it walks like a duck and quacks like a duck, then it's a duck. So if it has all the properties you want, if they ask me anything about it, for example, all the complex valued points, all the points, closed points, they are what you think that you can give a bijection. Let's do projective space. You can find all the points of the variety using mSpec and realize they are in as natural as you want, bijection with what you want, of n tuples, n+1 tuples of complex numbers, not all zero, up to multiplying by a scalar. So it exactly captures what you want. But the problem is not knowing what you want. Maybe a different way to say it is this, which is let's just do complex, let's do manifolds, not schemes. And I'll claim, because my definition of projective space works just as fine there too. And the great thing about my definition of projective space is the thing that would concern me about giving it a manifold structure by using my ceiling is that other people have different ceilings and things are pointed in different directions. How do I know they all agree? Well, now all I need to do is show that they agree with with this one definition that I gave here. And if they do, then they all agree. So it's a really cheap way of gluing together things or making things agree. It's just like a universal property thing, where if you describe something in a universal property way, you know, you really can nail down what it is. And maybe the last thing I'll say is, I don't think this is the right definition of projective space. Like the best definition of projective space in retrospect is not what you think it is. It is, and it's sort of you realize what it's trying to be, and you make it say it in a better and better way. And eventually it gets distilled down to something very simple. And so I will now tell you what projective space is in a way that this is one of the few times Jonathan will agree with things I say that I think, and it's which is, well, what's a map to projective space? It is the data of a line bundle, whatever it is, that is, in a bunch of an n+1 sections, not all zero. So that's projective. That's projective space in that's projective space in the way that people normally. That's the version, the way people normally think of it. Or if you want to make projective space out of a vector space, I would even then want a line bundle and then a map from that vector space to. Well, let me just stick to projective space in the classical sense. That this is that's
yeah. And if you want to read about that, that's in Eisenbud and Harris. They go through this in like a ton of detail.
Right.
Perspective.
And the point of this detail
actually useful too.
Yeah, I feel like what you're trying to get from that is really point of perspective, not like there's no. You think about it long enough, and you make the content go away.
All right. Okay. So okay. So another question was, so when you have when you write a scheme as the union of two principal open sets, right? Is it true that the O of the union is the categorical pullback of the two ring of functions over the intersection? I actually didn't really. So
the meaning of that is exactly the sheaf condition. So the answer is yes. Because if you translate what that means, that is literally exactly, you want two functions that agree on the over. Yeah, that's exactly right. And that works with any number of, let's see if I say that correctly. Yes, I think that's right. That agrees with, yeah, and that works with any number of open sets. I think that, I would even forget the scheme thing. That's for sheaves more generally, if I understand the question correctly. And I'm not.
Yeah. I think yeah. I mean, I just write down the equalizer diagram, so I don't know. Yeah, that was, I guess it's a good exercise to do that in P1, maybe.
Yeah.
With those two open sets to see that it actually gives you the constants. Okay, so then there was a long discussion of why are we always dealing with triple intersections? Okay, and so you were asking about, so this is a good segue, and so someone asked, there's an analogy with Van Kampen in that you only need triple intersections, and why is it always you only need triple intersections? And then Jonathan said some stuff about descent, and I forget what, I don't know. Jonathan, do you want to add more stuff to this? If he's here, or maybe being attacked.
Yeah, I'm here. I don't know if I want to. I don't know. Is there enough of a question there already, Ravi, or do you want me to say
Well,
something.
okay, maybe I'll say something and then you can answer what it is. Like I should say, the reason I find, let me just restate the question, sort of highlight what's interesting about it and why, which is and why it was asked, sort of, which is why when you are trying to glue things together, and again, I may have said this before, descent is another word for gluing. So if you want to, if you extend your notion of gluing appropriately, I guess, that it's this strange, it's this fact that it's mysterious how sometimes you have to go to double intersections, sometimes to triple, and then why do you have to stop at triple, and for some constructions and doubles for others, and then the really scary people will be going into very deep, like even things you need to go deeper in for intersections. And so like, why is the identity axiom you only have to go to double intersections? For gluability triple, do you not have to worry about, wait, am I doing, no, sorry, identity you have to go into singles. Gluability, for gluability you have to worry about double intersections. Gluing ring spaces, you have to go to triple intersections. So Van Kampen, I must admit, I always forget which one, I forget names of theorems. So I will
Van
say,
Kampen is the fundamental groups where if you have two open sets, then I guess if they intersect on trivially, then the fundamental group of the union is the free product of, is it the
Beautiful.
union or the
yes, in that case, I can, great. It fits exactly into the story, right? Okay, why you have to go that far, no farther? Yes, I feel like all I can, what I want to say to sort of segue into Jonathan providing enlightenment later on, is yes, and I find it, I literally do spend time like when I'm wandering around thinking about things as to when you have to go to double or triple, and to try to set this up in my head where I can really understand what's which way to go. And I can say things and then they become more and more formal the more I try to distill them. And then in some sense, less and less comprehensible to the outside world, but more and more comprehensible to me. So I think Jonathan's already gone down that rabbit hole. So maybe he's the best person to, do you want to, I mean, can you say anything? Is it possible to say anything as to why?
I can repeat what Jonathan said. So he said that Van Kamp is an example of descent because actions of the fundamental group are covering spaces. So Van Kampen is a descent for covering spaces.
Right.
And I don't really understand what he means, to be honest.
Well, so for that comment, it was just saying that you can understand the fundamental group in terms of covering spaces.
Yeah, for sure.
They contain the same information. Yeah. So
fundamental groups are so for people don't remember that fundamental groups are the deck transformations. So the automorphisms of the covering space is the fundamental.
Let me say more with what, let me say a more general setting where this somehow becomes less surprising because it's more general, which is if you have a topological space and you have like a map to it. You want to understand like family, which I usually think of families of things, but you have just a map from, you have a topological space U and you have some map to it. If I tell you what the map is, I've got something here mapping to one of the open sets, and I have something here mapping to another open set, and I want to realize how they glue together. I need the additional information of how having a map to U and a map to V doesn't tell me how to get a map to U, even if they do glue. There may be multiple ways of gluing them. And so there's this extra bit of information of the isomorphism or of the correspondence of the restriction of this guy to U intersect V and the restriction of this guy to U intersect V, and they better be able to glue together. So I need to give that information to tell you how to glue. Except I better, if there are 3 different open sets, my instructions better not contradict each other. Where over U, I tell you how to glue it to V and V to W and then W back to U, I better not have a contradiction. And so that requires a triple overlap condition. And a covering space is an example of such a thing. But once you pass the triple overlap condition, you're done. You need nothing else because you've built the resulting thing. You've described, if you want, what the points are. And the topological, and if you're talking about topological spaces, you've already defined the points of what you're mapping down to. And the topology you've already implicitly defined, so you know everything. So at least in that concrete case, you can see why you have to go to triple intersections. And it's because you have non-trivial isomorphisms. So this is an example of why maps to something form a sheaf, a fixed thing form a sheaf, but families of things form a stack. That's the a 2 sheaf, if you want. And then you can say, what is a stack? Well, stack is that. A stack is the sort of thing where you have just like a sheaf. What is a sheaf? It's the sort of thing which we abstracted away what we wanted a sheaf to be. You have things over an open set and they satisfy, and you can identify them locally the way we just defined. What's a stack? If you really want a definition, that was a definition if you squint a little bit in abstract. Is that Jonathan, or you is that okay? Is that
essentially, yeah. The point was just that because the covering spaces are the same information as the fundamental group, if you want to assemble the fundamental group out of local pieces, you need to figure out how to assemble covering spaces out of local pieces, and the conditions should have the same form.
That's a good way. Yeah, you can just
And I presume this is a proof. This would give a proof of Van Kampen if you say it the right way, whatever Van Kampen is. Yeah.
Right. Yeah.
Great.
There's
This
also
is Van Kampen.
that just appeared in the YouTube chat, which is that the cocycle condition that you see for this gluing is really the condition for the relation that you're using to glue with to be an equivalence relation. It's the transitivity.
Yes.
yeah.
Great. And then if you want to get right, the good thing is you can restate this in so many different ways that you can say, great, that means the isomorphism, the isomorphism things is a sheaf. It's there are all these things you can say in different ways that are all identical that mean the same thing. So I agree with whoever said it, and then you could somehow making them all. What I find difficult for me, or fun and interesting, and the challenge is sort of taking these different things and trying to make them the same in my head. So I just automatically see one and think of the other without just by muscle memory, not with conscious thought.
All right, so I got another kind of a question that I didn't know how to answer. So is there a sense in which generic points, so this is from Dean Baskin, okay? So is there a sense in which generic points are encoding some finer or coarser homological or homotopical or other globalish data? So you're talking about generic points of schemes.
I'm not sure what to say other than yes, because there is, but how you extract information can be a bit tricky.
I mean, there's always like generic fiber of over, if you have a family over some, I don't know if that's what he means though.
Right, and then how they actually, I mean, maybe an example, and this is maybe for someone like Dean who knows about vector bundles and line bundles, that generically over the generic point, all line bundles, a line bundle is just trivial, mostly. Like generic means mostly in some sense. So all line bundles are locally trivial. So you need the additional information, not just what's happening at generic points, but also how it specializes. And now we get a little bit into Jonathan's, into this issue of how things, so there's a lot of information there, and how you extract it is,
or maybe it comes up in semi-continuity arguments.
Right.
Yeah.
I'm not sure what you mean. It sounds like you have.
Well,
I mean,
if you got rid of the generic point, so if you in your topological space, if you got rid of your generic points, all the semi-continuity arguments would behave differently, you know, because
although they still work the same. I mean, you could. I mean, in some sense, with varieties, there's no additional logical information in the generic points. There's nothing you can prove with generic points that you couldn't prove without, which is not contradicting what you said at all. It just means that but although in that case, even there, it's a psychologically important crutch. Like it's useful to say, I mean, one thing which Dean would automatically agree with is that if you have something, and if you have like a manifold and you have a boundary that's codimension 1, that you really think of it as just like a curve, like as you want to say somehow that like this high dimensional thing and this high dimensional thing that's in codimension 1 kind of really looks like just a curve with a point times cross something else. And somehow you want to be able to say, oh yes, that's like a codimension 1 thing. And I don't know how to, I mean, with the word generic point, you can say, great, that generic point is codimension 1 inside everything. Whereas any individual point, you don't have that. So it's a way of catching that information. This is useful, but not logically.
Raleigh, here's an idea of an example where maybe the generic point captures some homotopical information. So if you take a curve and take two closed points and take the intersection of all open neighborhoods of those 2 points. So that should be the spectrum of the semi-local ring. Has 2 maximal ideals. If you just look at mSpec, you just see 2 points and it looks disconnected, but they're connected through the generic point. So you need the generic point to see the connectedness.
That is good, and that's capturing
way,
the paths, and that's capturing all the paths between those 2 points on your space.
So I'm looking at the questions again. There's another question. Is they wanted a kind of a recap of how we found the generic point on CP1 again.
Ah, great. Well, we know the generic point on A1. So there's one and there's only one. And there's one on the other A1 that we're gluing to it. And we glue them together. I just need to tell you which points here glue to which points here. Like the gluing is a really dumb, it's a gluing of sets. So the thing to say is that all the fancy stuff comes along for the ride from the sets. So the question is, when you glue those 2 things, you have if you remember, the green glue is on most of it, and the generic point had glue on it. And on the other side, the generic point had glue on it because everything in that open set had glue on it. And the generic point isn't every non-trivial open set. So when we glue them together, they were the same thing. And so that means that there's only one generic point. And so by gluing, there's only one. And then if you define P1 in a different way, like the other question of the other way to write, then you have to at some point give it a scheme, give it a topological space structure before you can use the phrase theorem. Yeah, I'm not sure exactly what to say other than that. The important thing is that in any case, the gluing is so explicit, you can see what the generic points do.
Yeah. All right. Okay, so there's some more in the chat. There was one thing that I saw that you keep mentioning Hartog's theorem. Maybe you want to say some words about Hartog's theorem?
Sure. Hartog's theorem. Okay, to be honest, I'm not sure the very precise statement of Hartog's theorem, but I think it's something like this. I used to know that if you take it's in complex analysis where if you take like you're inside, it's a local question. You're inside C to the n, and let's say you have a analytic closed subset. So I guess that means cut out by a bunch of it's cut out by a bunch of analytic equations, and it's not codimension. I guess how's the best way to say it? Its codimension is bigger than 1, or if you want, there's no well, define it however you want. Figure out how to define it. Then any function defined away from this codimension 2 subset extends over. So in fact, so a priori it may not be. So for example, 1 over z is defined everywhere away from z equals 0 in a one-dimensional complex world. But if you have a z1 and a z2, there's any function you make that's defined near 0, 0 has to actually extend. And I guess you do it with you could do it with some clever, I guess you do it with some very clever integral to produce what the value is.
Yeah.
And in particular, if you study complex, I should say then, if you study complex, a lot of people are having the complex analytic point of view very reasonably. There's a Hartog's thing that should work even for singular complex analytic varieties. I'll even say what that translates to, which is you don't need smoothness for this to work. You don't need C to the n. All you need is that it is normal. All you need is that the local ring is integrally closed in its fraction field. So it's actually secretly an algebraic, not secretly, it motivates. It's not like the algebra is telling you the complex analysis. The complex analysis told us the algebra first.
All right.
So, go ahead, Taylor.
Okay, so here's one. So defining the structure sheaf at general open sets doesn't work the same way as distinguished open sets. But since Ravi already said what the stocks are, we can just take compatible germs and define compatibility using the basis. Is that correct?
That is completely right. And then you might think, why didn't we just do that for the entire structure sheaf? But then you have to still show one thing, which is that the sections over the distinguished opens are what you think they are. So there's no way around one painful gluing thing to do, but it needn't be so painful. I do think, for example, Hartshorne's way is to get around things is painful, but the earlier Sarah way was not painful. Like Sarah is like Sarah's like a major deity in the pantheon of, but yeah, so you have to check. And I think this is what Sarah actually does. And you don't need Noetherian hypothesis. There's nothing about, we never use the word Noetherian ring in any of this, but you have to then check that if I have something, if I give you an element of A sub P for all P, and they're compatible in the sense that you have to say precisely what you mean, why do they come from an element of A? And the answer is, well, and then you're going to do gluing. No matter how you say it, you're going to have to prove the same thing we had to prove. Because what you'll do with compatible stocks is you'll say there's an honest open set, and you have a bunch of honest open sets, and then you need them to cover spec A. And you're going to be heading, you're being funneled through the same, you're being funneled through the same passageway. But yes, it's a very useful way to think about things.
All right. Okay, so one question was, so there's these two ways you glued A1, right? And so they both yield the same topological space. So why is one Hausdorff and one not?
Great. No, they do not. They can't, because you can't get one topological or one not. And the answer is, if I give you two pieces of paper, like I give you two discs, and I glue them together in the following two different, like if I erase a point on a disc, it looks like a cylinder, right? So it's like so maybe think of them as like a cylinder with a cap on top. And if I glue them like this, I get a sphere. I get CP1 if I'm in the complex setting. But if I do instead, I glue them like, I don't know how to describe it. It's hard to say. If I glue them in a different way, it's like, take C star, takes the complex numbers minus the origin. And now I'm going to tell you, I'm going to put the origin back in. So in the case of P1, I put one origin as t goes to 0 and one as t goes to infinity. In the case of the affine line with the double origin, I'm putting both at t equals 0, but I've declared them to be different. So they're like two limits as t goes to 0. You can go to like the T0 guy or the U0 guy, and that's, so they are topologically different.
But Ravi, in the Zariski topology.
Oh, Zariski, oh crap. Yes, the Zariski topology, they are true. But the important thing is that the Zariski topology is very blunt, and you need the ring. You need the sheaf of rings. So in fact, once you have the sheaf of rings, then the Zariski topology, then they are no longer isomorphic. That's a true, yeah, that's a true statement. Yeah, great. Yes. So you can't just, Zariski topology is blunt, and you never want to think about the Zariski topology by itself. You really want, I mean, the Zariski topology is deliberately blunt. So all the information, so much information can be carried on the rings. And when you want to carry more topological information in the topology, as Jonathan said, there is a lot in the Zariski, but then in the Étale, there are things that are more akin to the classical topology, like the Étale. And then there are things that are less akin, but are very useful. But there are things that are mysteriously akin, like the smooth topology. And then there are things that are less akin, but way more general, like certain flat topologies. I don't know what the phrase "the flat topology" means, but at least I know what the various flat topologies.
And I think the point was that it's not literally the topological space that's not Hausdorff. It's, I mean, that is also an issue. It is also, I mean, for every scheme. But
right, so I should say, right, if we take the official definition of Hausdorff, the wrong definition of Hausdorff, then none of them are Hausdorff. Like A1 is not Hausdorff. Yeah. And that's just because we're using the wrong definition. And there's a right definition that even still works for Hausdorff. Like it's just that the definition you're being told was designed for only very nice topologies. But in fact, the right way to say it works for arbitrary topologies.
Yeah. So I think that's good, unless anyone has other questions. All right.
Okay, well, maybe then let me end with a semi-question related to that, which is parsing for people in other fields, which is, for me, one lesson that one learns when thinking about a lot of these questions is the importance of the diagonal morphism. If you have a map from x to y, maybe first if you just have one thing in some mathematical setting, often mapping x to x cross x is an important thing. And then slightly more generally, if you have a map from x to y, the diagonal map from x to x cross x over y ends up capturing a lot of things that you didn't realize were being captured there. And Hausdorfness is a property of the diagonal for me. But I feel elsewhere in mathematics, there should be something which, at least in retrospect, there should be some like differentials turn out to come up from the diagonal, things like that. So I'm just very curious. I would like to know if elsewhere the properties of the diagonal are, I'm sure in topology, in like this is even more true than in algebraic geometry because it's somehow closer to the source of all things. But I'd be curious in other parts of as well.
All right.
So in that case, so I think we're good. I'll before too long post the edited version, but of course before I post it, it's here. I guess many things I've not done yet, such as I was going to put the question period and have it available somewhere, and I've yet to even think about how to do things like that. But it's of course still up until I edit anyway. And I actually a lot of things on Zulip I haven't even been able to, I haven't looked at. So I feel like I want to, in past weeks, I've responded to things and it's been very interesting. But now that the Stacks project workshop is over and my period of subservience to Yuan de Jong is paused a little bit, then I can get back to Zulip too.
All right, thanks.
Great, thanks a lot. And I'll see you all online or next week. And thanks, Shepherds, very much again.
Yeah, no
Thanks,
problem.
Bobby.
Let me stop YouTube.